So this is the outline of the talk. So I'll tell you a little bit about my university. So I'm close by. I'll show you where I do. I'll tell you a little bit about what I work on, my new book I just published about a year ago, and then going into this idea of weak continuous measurements. And I'm going to connect it at the end to this question about optimal control theory, which I think is also of great interest to many people in the room. And this is really focused on quantum systems. So the theme of the conference is non-commutative stuff, right? And so this is calling out for quantum physics. Okay, and so this is some of the work done with former students, Tatha and Phil, that have gone on to be postdocs in Berkeley. Good. So where is Chapman? So here we are sitting up here at UCLA in Los Angeles. Chapman is in the city of Orange, which is right here, near where Trifon is in Irvine. Its closest proximal landmark is Disneyland. So if you've ever been to Disneyland, that's close to where the university is. I live down here in Laguna Beach where all the little hearts are, and that's my school. And so I direct this Institute for Quantum Physics, and so please come visit me if you're ever in the neighborhood. The things I work on, so be talking today about quantum measurement and control. That's really one of the themes of my group for the past, 20 years or so. I also work a lot on metrology, so the science of precision measurement, so using quantum physics to make better kinds of detectors and new kinds of paradigms and resolution, trying to beat resolution limits in both the optics and in the radar. Then I also work on topics in quantum thermodynamics, so mesoscopic thermoelectrics and so on and so forth. And then also my institute is really focused on foundations of quantum mechanics. So that's a little introduction to my interests and background. And so now let me tell you a little bit about, I'll mention my new book. So if you're interested in the things I'm talking about today, you can go into a deep dive into this book I published with my colleague Irfan Siddiqui at UC Berkeley, published by Cambridge about a year ago. Okay, so that's called Quantum Measurement Theory and Practice. Okay, good. So let's go a little bit into types of measurements from a slightly more mathematical degree. So for textbook measurements, you would describe these mathematically with some set of projection operators on a Hilbert space. And so what the formal contribution that quantum theory gives us, it gives us a probability assignment. Given a quantum state rho, the probability of some outcome j would be the trace of rho with a projector, and projectors do what projectors do. But there are other kinds of measurements where I'll be telling you more about. And so if I have a generalized measurement, this is something where you have an imperfect correlation between the system and the meter. We describe it not with a projection operator, but with some more general positive operator, E sub j. The probability assignment still looks the same, but now there can be many more outcomes, or many fewer outcomes, than you would have in the dimension of the Hilbert space, whereas the projection operator, that spans the Hilbert space of the system. And for the jargon, sometimes we talk about a weak measurement, and so this was when I have this positive operator is almost identity, but there is some small correction that's proportional to some system operator A. So now the probability of the result is some detector-dependent stuff plus a small contribution that involves the system. And so typically we describe this with some weak coupling between a system and a meter, and I'll talk more about that in a moment. So that's sort of a brief mathematical recap of measurement theory. And the important thing is once we make this generalized measurement, we have to understand that in quantum mechanics, when I measure the system, I disturb the system. So I have to then take into account that measurement back action, and there's a mathematical rule that tells us how to do that. Given this decomposition of this operator in terms of these measurement operators, I would write down some little formula like this, which is analogous to the Bayes rule. If I think about rho as some prior distribution, the outcome j is some data that I acquire from my detector, and then rho j would be something like a posterior distribution, but now generalized to a quantum setting. Okay? And the way you typically would realize that in some experiment is you would have a system you're interested in, some meter, you let them interact via some, say, Hamiltonian. You would do a traditional measurement on the meter, getting some outcome, definite outcome, which then implements one of these generalized measurements on the system. Okay, so this is a little model in terms of entanglement with a meter. Okay, now we start getting into the theme of this meeting. So one of the other types of measurements we talk a lot about are continuous measurements. So if I'm monitoring a quantum system continuously, these sort of come in two different flavors. One is a diffusive type measurement, where I'd have some measurement record as a function of time that I acquired data from my experiment. And then associated with that is what we call the quantum trajectory. So then we reassign the state at every time step to a different value, and it has a diffusive kind of motion like a Brownian particle might. So this is a diffusive type measurement, so I have a quasi-continuous stream of data coming to the observer. But the other kind of detector we have is what we call quantum jumps. Maybe you've heard of these quantum jumps. And this usually happens when the detector has a click, like a photodetector. And so this is an example of some experiment where you have these fluorescence counting going on and off, on and off and off. And that corresponds to quantum jumps of the quantum system. In this case, it's some 3-level quantum system. The important thing I want to stress is that both types of these measurements allow us to track the quantum state in time. So it's no longer the quantum state was this, I do a measurement, it's now collapsed. And now the collapse process becomes dynamical and continuous. And so I'm going to give a little bit of physics, and so bear with me through the physics, but I want to motivate this from actual data and devices, and then we'll get more into the mathematics in a little bit. So one simple example is this kind of a quantum system where I have a two-dimensional electron gas, so it confines electrons to a plane, and then metallic top gates to then further constrain the motion of the electrons. So electron, for example, can be on the left dot or the right dot, or can tunnel back and forth between them. And the way we measure the location of this electron is with a nearby conductor. So I can apply a voltage between a source and a drain, and the current flows through this little channel, the so-called quantum point contact. And the reason I can detect it is because the charge of the electron slightly changes the transmission of this quantum point contact. So it becomes a little bit more, a little bit less transmissive, so the current is either I1 or I2. Okay? But the interesting thing is, when you examine the physics of this detector, the current itself here is a noisy thing, right? So the electrons try to come, sometimes they get through, sometimes they reflect, and so there's an intrinsic source of noise for the detector that's called shot noise. And if I look at the spectral density of that shot noise, I can then form this dimensionless combination of the scales. So the shot noise density, SI, divided by the difference between these two currents squared, there's a new time scale, and that corresponds to essentially getting signal-to-noise ratio of 1 from this detector, so I can then reliably tell is the electron on the left or the right side. Okay? And so in the theories of quantum measurement, these continuous quantum measurements, this time scale becomes a fundamental new time scale that describes the dynamics of the quantum system.
Okay. Can you tell us what they really measure at the end of the day?
So what they're measuring is they're measuring some electrical current. Okay, so they have some noisy, time-continuous electrical current.
Up and down, or at the side, or?
Yeah, so in this case, you would apply voltage across the source and the drain. So that's where your battery goes. And then you have an electrical circuit that goes like this.
You measure outside.
Yeah, and then you have a detector, and you're recording, in principle, the time-dependent electrical current. Exactly. Yeah. So these are actual devices people build in the laboratory. Okay, but yeah, so the point is we have this new time scale in the system. To give another physical example, I work a lot with these things called superconducting circuits. So there's a whole industry that is based on superconducting Josephson junctions as a quantum technology. And so there's a major industrial effort both at IBM and Google, most of the major players, trying to build quantum computers based on these electrical circuits. So if I just had an LC circuit and I quantize it, you would have levels, energy levels that are regularly spaced. But if I put a little insulating element between the two superconductors, I get a Josephson junction. So I have antiharmonic levels, so I can address those antiharmonic levels using radiation, for example. All right, and so we use a lot of these kind of systems to be able to do these experiments. And so to give an example, one such superconducting circuit looks something like this. I put in microwave radiation into some aluminum box with one of these little circuits inside of it. There's a off-resonant phase shift acquired by that light. It comes back out. There is some special dedicated amplifier that operates near the quantum limit to amplify that to that signature. And then what happens is that depending upon the initial state of the cavity, this is a quadrature plane. These are the levels of the quantum qubit. I get a slight shift in the quadratures, which will amplify them. I get some histograms that look like this or like that, which allow me to tell is it the red level 1 or the blue level 0, corresponding to these different histograms. Okay, so that's another physical example of how this works. And so at the end of the day, in this kind of experiment, you actually get some digitized voltage that you acquire as a function of time. This is analogous to the current that I was showing. And then if I integrate that signal and histogram it, I get this kind of partially overlapping distributions. So I know, for example, if I get an outcome that's way over here, I'm very confident it's in the blue level. If it's way over here, I'm very confident it's in the red level. But if it's here, I go, I don't know. It could be this or it could be that. I have some kind of probabilistic statement. Okay. So that's how these experiments work. And now let's go further into the quantum physics. So the interesting thing is that once we have this physics, we can begin to write down equations that look something like this, that look a little bit like things you would see for Brownian motion. There's some kind of mathematical Wiener process, so there's a deterministic drift part, and there's a stochastic contribution as well that depends on the state of the system. And we can then be able to take the data we acquire from the system, condition the evolution on it, and then be able to do this kind of movie I'll show you. So if we start, for example, so this, I should tell you, so this is the block sphere representation of a two-level system. So sigma x, sigma y, sigma z, these are Pauli matrices. And so this would be a representation of the quantum state. So this is like a preparation of the ground state in the first excited state, a superposition with this phase. And as I turn the detector on, we can write down this kind of quantum trajectory. So this would be the conditioned quantum evolution as a function of time. And you see eventually it's going to collapse up here to the sigma z state, okay, as a function of time. So this is like collapsing to the one of the eigenstates, but in a dynamical way. So I can actually track the state as a function of time. And this is really nice, I think, because it's now we no longer have a kind of a mysterious understanding of quantum measurement. This is really a dynamical process. We have precise mathematical prediction over what's going on in the guts of the collapse process. Okay, good. So we can. There's lots of experiments that have been done now, so you can actually track single realizations of the quantum state and then tomographically check that is an accurate prediction. I can go more into the details of that if you want. I think I'm going to try to get a little bit more into the mathematical portion, but this is just showing the data from experiments that we have good ability to predict these things. And the analogy I like to give is if I had a bunch of butterflies, and I think about those as different realizations of the experiment, I can release them from a cage, and they land on, say, one of two trees. It lands on the left tree or the right tree. This would be the old way of describing it. But now with this more dedicated resolution of our detectors, we're able to actually track the path of these butterflies as they go from the cage to one of the trees. You get much more detailed information. Okay, and so if I go further into this, we can begin to make contact to some of these things like Schrodinger bridges. Yes, you have a question?
Yeah, to expand on the analogy. So you say you're tracking the trajectory. Are you tracking the trajectory of a single shot of the circuit?
Yes.
Okay.
Yes. So if I go back here, if I look carefully at these, so this is, the upper levels are ensemble averages, but down below, this is a single realization. So for example, here I'd be collapsing to z equal +1, for example. And this is actually as I start driving the qubit as well, so I'm driving it. And so that, if you look carefully, there are actually two different plots there. So one would be the state of a single run, and one would be what we call the tomographically validated version of that, where you do this millions and millions and millions of times and collect reams of data, and there are statistical ways to be able to check that that's the right state. So that's the validated trajectory as well. Does that answer your question?
Yeah.
Good. All right, so let's get more into like this Schrodinger bridge stuff. All right, so we imagine we have a system, let's see, and I prepare it, say, in the green state that I was talking about before, and I run the experiment one time, and I get some particular current output like this, and I end up at the end of the day, say, in the red dot. Okay? Now, if I did that again, a second time, I prepare the same experiment, preparing it in the green dot, I do it again with the same time period. We know from quantum mechanics that identically prepared initial conditions give rise to different final outcomes. That's the weird thing about quantum mechanics. So I might get this trajectory on a second realization. But I can do this again and again and again. And I get many possible final states with many different possible ways of getting there. Okay, so it's like a Brownian type of motion. But I can ask a different kind of question. What happens if I focus on only the subensemble of trajectories where I start and end at the same state every time, right? So this is like the Schrodinger bridge where I pin my endpoints. I can think about post-selecting just on this red state, the ones with this red state. So that may be another one that ends in the same state, but it's a different trajectory. And here's a bunch of them, okay? So it's all start and end at the same place, but go through different paths on the way there, okay? So let's think about this kind of situation. Of course, not everyone will do that, but some subensemble will. And now we can ask ourselves the following question. If given that we start at one state and end at the other at some time t, what's the most likely path connecting the two states? Right? So this is the question I want to answer, and it suggests some kind of action principle. And of course, action principles are really important in physics. It tells us like why light bends. This is Fermat's principle, the principle of least time, if you have a mirage, for example. It's also really important in, so this is like the optical Fermat's principle. It's also important for mechanics. You have a Lagrangian, you minimize some action. That tells you also the equations of motion. And importantly, when I solve these equations of motion, I can set the initial conditions, the initial momentum and position here, for example, or I can do some kind of mixed boundary conditions. I can fix the initial position here, but also the final position, for example. Right? So we're going to do something similar with our problem. And so this, we can come back to the problem that I gave. What's the most likely path? So what we're going to do is something like this. This is now a path not through a classical phase space anymore, like you would have for a Feynman path integral, but it's a diffusion through the quantum Hilbert space. Okay, so we want some kind of stochastic path integral for this physics. And so this is what we worked on. This was, I think, our first paper was in 2013 about this. And the idea is simply to write down some path integral. Now this is a stochastic path integral. Let me tell you a little bit about the ingredients that go into this. So first of all, these Q variables would be the quantum state or parameterization of the quantum state. R would be the readouts you get in your device. And then we introduce additionally some auxiliary variables, P, okay? And the P's are analogous to momentum, but you can think about them as Lagrange multipliers. They essentially impose that quantum back action rule I was telling you about, and we can also take into account the probability of the outcomes, okay? And so what is the script P that I'm calculating? It's simply the probability density of all possible quantum trajectories that takes into account both of the outcomes as well as the quantum states. And so we can write down this formal action that involves the dynamical term here with this first term, and we call this the stochastic Hamiltonian, and that takes into account the probability of the detector outcome, the quantum back action rule, and so on and so forth. Okay, so that's tailored then to the kind of measurement you're doing. And so this is a kind of a double space which has a canonical form to it, and then we can express this joint probability of all the results of the trajectory as the path integral. Now what's interesting is if I do that bridge problem, if I fix the initial and the final conditions, and I extremize my action, what I find is I get some ordinary differential equations. It's analogous to something like a classical path for a Feynman path integral, but has a very different interpretation. So the interpretation here is, for example, if I start in that X eigenstate and I collapse, say, down to this state over here at some time t, I have many different possible paths to do that with this histogram, but the most likely one is going to be the one that minimizes this action, and that's going to be this yellow dashed line, okay? And so you actually see there's actually a magenta line. That's actually data from the experiment that they did to be able to verify that. And you see you have a very nice agreement between the experiment and the theory, showing you the most likely collapse way to go from this point to that point. Okay, so this is this formalism that we've developed. And let's go talk a little bit more about the formalism. So there's another way of doing this called the stochastic master equation or stochastic Schrodinger equation. We can show there's an equivalence there. This is like a complementary way of doing calculations. It gives us a new way of calculating some correlation functions or averages as well. And it has this interesting canonical structure. So we think about P as like a canonical momentum, Q, which is the quantum state, is like the coordinate, and the stochastic energy I was talking about is like a constant of motion. And so we can use so many of the formal tricks of Hamiltonian theory to be able to calculate things as well. Okay, and so this naturally suggests the answer to the most likely path question. It's the saddle point approximation to extremize this action, which is our action principle. Okay. And then we can also then generalize this. We can do feedback. We can include dephasing, things like that as well. Okay, so good. So the takeaway point is the action extremum then gives Hamilton's equations as the dynamics, which we can then solve using conventional techniques. So we can then compare that. Let's see how this compares then to experiments. So if we do this experiment millions of times, we collect these quantum trajectories for these quantum bits, and we can verify that indeed that we get the correct experimental verification of this theory shown in these plots. We can also then drive the system at the same time. So if we measure and drive simultaneously, as you keep the initial and final conditions the same, but change the time between them, you get very interesting trajectories. Nevertheless, that the formalism is able to capture that with the different times as well. Okay, so that's more or less the most likely path story. And so I want to now switch gears a little bit and tell you about, okay, I think we're doing good, some new work. So this is just on the archive maybe a few weeks ago. And I want to tell you about how to apply some of those ideas now to do optimal control theory for continuously monitored quantum systems. And this will be closely related to these principles that Trifon and many of you have worked on. This Pontryagin maximization principle is closely related to this. All right, so let's dive into that a little bit then. So the idea is that now we're going to be doing a continuously monitored system. So we have our quantum system, we have our monitoring, collecting all the data from the emission, for example, of this atom. We can also drive it as a function of time. And the point is that we have different handles on this quantum system. We have handles on the unitary drives, we have handles on the measurements, and we're going to let those handles become time-dependent control parameters. And the idea now is we want to then try to drive the system, say from one state to another state in a given amount of time, and we want to find what the right control schedule is to apply to those parameters, those handles we have in the system, to make it do so in an optimal way. Now, when I say optimal, what do I mean by optimal? I mean optimal in the sense that I maximize the probability of success, and that now you begin to see why this maximization principle I was talking about is related. Okay, so we're going to optimize the probability of the outcome as the cost function, and this is indeed related to this Pontryagin maximization principle. Okay, good. So you guys don't need to know this, but I'll say it anyway. They say there's a nice expression: never underestimate the pleasure someone gets of telling you something you already know. Right? Okay. So the idea is we have some mass transport problem. We want to have our piles of dirt from point A to move it to point B in some optimal way. And so this Pontryagin maximization principle is one method in optimal control theory to find the best possible control for taking a dynamical system from one state to another, especially in the presence of some constraints on the system. If you have constraints, it's important to take that into account. And so one little example here, if you have a ferry, you have a river where the water is flowing from left to right with some velocity profile. I can change the angle of my boat as a function of time. What's the best way to get from point A to point B going across the river? We can solve that problem using this kind of principle. Okay. So we're doing something similar here, and now we're going to get into a little bit more of the mathematics. So the idea is we have some kind of equation. This is our stochastic master equation. It involves the Hamiltonian of the system, H. Rho is the quantum state. There are other operators. There's some jump operators involved here. There's V is the jump operator squared. This delta is the difference in expectation. And now the idea is that we're going to put some time-dependent control parameter. I'll call it chi as a function of time. And what might some examples of this field be? Could be some external magnetic or electric field, for example. It could be some kind of time-dependent RC drive. But it could also be a dissipative control. I could control which basis I want to measure my quantum system is. I can control an effective temperature, for example. All right. So we have some Lindbladian operator L chi, and then this R variable here. That's going to be my readout result. And so this is going to be the conditional stochastic evolution given some outcome R as a function of t, for example. Okay. So this is my starting equations. for my system. And now what we're able to do is then I can generalize this action I was talking about before. There's some kind of, so I introduce some new state, sigma. Sometimes this is called the co-state. This is analogous to that momentum variable I was talking about just a little while ago, but now written as an operator. And so I have a dynamical term and I have some other term, this stochastic Hamiltonian. It takes this particular form. So there is some kind of quantum back action term with this operator f. That was the one I introduced right here, this guy, the super operator. So I trace f with rho. And then this is like the log likelihood of the outcome. Okay, so I have to take into account that log likelihood of the outcome in this dynamical Hamiltonian as well. So it has the expectation of L, it has my readout operator. And remember that measurement time I was talking about before? Here it is right here. So it plays an important role in the theory, that time scale of the measurement, where I get a signal to noise of 1. Okay? Okay, good. So here's the central idea. The stochastic action plays the role of a cost function in this analysis. So what I want to do is I want to extremize my cost. I want to minimize my cost. I'm trying to maximize over the probability density of the outcomes. Now we have this time-dependent control parameter, chi, in our description, and the co-state imposes all these constraints. So to find the most likely readout, according to this Pontryagin maximization principle, the Hamiltonian will achieve the supremum for given rho, sigma, and chi, and I call R chi as the most likely readout. So if I'm extremizing over all those things to then find, what's the goal, is to find my control schedule. What's the best control schedule? Okay, so how does that work? Well, we all know how to maximize things. So we maximize over R, maximize over the control, maximize over the state and the co-state. And then we get a bunch of equations from that. So we get the most likely outcome for the measurement result. We get some constraints. This is just 2 of the equations. Okay, we can solve those equations. We're trying to find the interesting thing, which is chi as a function of time, to meet our constraints. We're starting at some initial state, for example. I end at some final state at some time. That's our constraints. And I have to find that control. Okay, so we can keep going. So if I write this out more explicitly, I get an equation for rho as a function of time. That's basically the original equation I had, but now R is the most likely path. The co-state equation looks very interesting, actually. So the co-state equation for sigma looks basically like something like a time-reversed version of the original state, which is, I think, fascinating. I think there's more to be said there. And so I have to solve these equations. And then when I look at my optimal, my stochastic energy, when I put all these optimal stochastic energies, I get some equations for this as well. These are expectation values in the angle brackets. So now these equations will allow us to derive the optimal time-dependent control chi of t together with optimal solutions for the rho and sigma, along with the readout. Okay, so that's a little bit formal. So I would like to unpack that with some examples. So let's go a little bit slowly through some examples. Okay, so here's a really cool example. So if I'm measuring a qubit, you've heard maybe of the Zeno effect, which is if I'm measuring the system strongly, but the system is evolving, has some natural evolution, if I keep measuring it, it will not let the system evolve. It freezes it in place. It's like the watched pot never boils kind of effect. But what you can imagine doing is you can imagine letting the angle at which you measure be your control parameter. Okay, so if I'm measuring like this, it'll tend to project it along this. If I'm measuring like that, it projects it along that. But I can imagine then taking my system, say I project it, I measure it here, and I start changing the angle of my measurement like that. I can start dragging the state along. Okay, so we call this a Zeno dragging effect. And so this is a way of incoherently controlling the quantum system. So if I try to, but then there's interesting dynamics there. You can say if I try to drag it too fast, maybe I lose it. It jumps to the other bases. And so indeed, there's some kind of interesting dynamics going on about how quickly I can drive that system. So if I have here this initial state, you see here that these histograms are various realizations of trying to drag it from point A to point B. And you see if I drag it slowly, I basically pull them all along with me. But if I drag it too fast, I see I get some escape population. So some of it drags with me, some of them escapes down here, which is bad. I don't want to do that. That's suboptimal control. So, yeah, so the measurement axis is represented by the white lines, while the theoretically calculated natural jump axis is indicated by the red lines. Okay, so there's some interesting dynamics here at play, and so then I can ask the question, if I want to go from, say, this initial state here to this final state there as a function of time, what's the right control schedule? How quickly should I move this measurement basis as a function of time? So I'm going to apply this formalism I've just told you about to calculate this problem. Okay. Good. So in this case, our Lindbladian operator is there's some measurement rate gamma here. Sigma x and sigma z are Pauli operators, and now zeta is the measurement angle. Okay, so that's the thing I'm going to control. So I can measure along any axis I want. So if zeta would be 0, I'm measuring sigma z. If zeta would be 90 degrees, I'd be measuring sigma x, and I can measure some combination of those operators. So when we go through this formalism I was telling you about, we can think about theta being the polar angle on the Bloch sphere. Here I've changed my notation a little bit. Lambda is the conjugate momentum. And so the stochastic Hamiltonian has this form. It involves the measurement rate, but it also involves there's a drive, omega. There's also a Drawby drive, rotating the qubit on its own. So it has some combination of all these degrees of freedom. Okay. And so now zeta is the thing I want to try to then find as a function of time. So when I take a derivative of this, when I extremize this Hamiltonian with respect to my control parameter, I can then solve explicitly for what the control parameter is. So I start at theta I as a function of t. If I just had uniform evolution, I would just have this term. This is like constant velocity t over the total time of the experiment. That's the final result. That would be done. So that would be the sort of the naive guess. But you see there's this additional term too. There's this arctan of the difference of the angles divided by the duration. The measurement rate shows up, the drive shows up, the measurement rate. So this is a kind of a tricky contribution you wouldn't have guessed that you have to include. And so this then tells me the optimal control schedule I need to apply to my angle to be able to achieve my task. Okay?
Can I ask a question?
Sure, of course.
So I mean, when I talk about the master equation, I write it down on the level of densities, right? But I think these coordinates are all written down in the coordinates of the Bloch sphere. Is that correct?
That's right, yes. So
One has to keep that in mind. If not, we are not seeing a connection, right?
Yeah, that's right. Yeah, so these are for Bloch coordinates, right? Yeah. So that would be like the quantum state point of view.
It's parameterization, and then
you parameterize the state, exactly.
You get different differential equations.
That's right. And so in the beginning, so when I started in a more formal way, right, this is a non-parameterized version. Here it's completely general. Rho is just rho. But to actually solve something, usually I have to parameterize it in some basis, right? And so now for this example, I'm doing it in the Bloch sphere basis. Exactly.
And another question, when you say drive, this usually refers to the Hamiltonian part, right?
Exactly.
I mean, that's something we have to learn if you meet this. I mean, if you talk to experimentalists.
Yes, so usually
drive is never the jump.
Yeah, that's right. So the way they do the drive is they typically have some coherent tone that they're applying at some given frequency, which is resonant with the qubit, and that gives this Rabi drive, right? So that's something that they can control. So if you increase the power, you speed it up. If you lower the power, you slow it down.
That's what they really can control.
They can control that, and they can also control the measurement rate. So this parameter gamma, right? They can control how strongly they're measured. Basically, how many photons they put in their cavity. That increases the measurement rate. Okay, so they have a lot of control over many things. It's really a very well controlled system. Okay, let me return. So this was sort of the simple-minded thing. This is the tricky thing you wouldn't have guessed. Yeah, and so what happens is, so this implies that one should not put the measurement axis exactly on the expected instantaneous state, but rather one should set it ahead of it. So you have to leave the system to get the expected angle of the. So we're learning things about the physics from this thing. Okay, and you kind of see that here. So the peak of this. So if you look at the peak of the distribution, so the magenta distribution is the distribution of the solutions, and you see the peak it lags a little bit behind the diabatically moving measurement axis, and so the optimal controls will explicitly compensate for the offset. Okay, so you see if this is like the instantaneous axis, you see it lags behind a little bit. Yeah, good. All right, how am I doing? Okay, we're doing good. All right, so let me give you another example of this optimal control. So here's an example using an oscillator. So before I was talking about two-level system, now this is an infinite system. So this is a monitored quantum oscillator, x squared plus p squared. And what we can imagine doing is measuring, you would take the quantum system and you would measure in some particular quadrature. Okay, so I could measure either the position degree of freedom or the momentum degree of freedom, or some combination of position and momentum. Okay, so now theta of t now becomes the quadrature angle that I can measure, and that's also going to be our control parameter. All right, so this is the measured observable, right? This is the complementary observable m, and then we can similarly write down these. We can parameterize the system. We can write down optimal path and costate equations, solve together simultaneously for this control parameter, theta as a function of time. Okay, so here are some of the equations that pop out of this. Okay, I'm not going to, okay, so there's some VWZ that I define like this. Okay, so now I have to solve these equations together. And when I do that, we get some nice, simple, relatively simple behavior for some cases. So we would go, this is position starting from the right initial position, in the final position with control. This is the optimal momentum, optimal readout, and this is the optimal angle. So this is the thing I would need to apply as a function of time. So this is the control schedule I need to apply to make it go to the final point that I get to choose. Now what's interesting is that when there are certain cases where if I imagine my control is limited, I cannot apply whatever control I want, but let's say I can go between two values of the control. That's an experimental constraint. What happens is that when you start solving these things numerically, this optimal control starts doing something like this. It goes down, 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 and then, oh, jump. There's a sudden jump, and then it goes smooth, jump, smooth, jump, smooth. So basically it's saying I take my control, I vary it a little bit, and then slam it over to the other side. It go like this, slam it back. So in physics, we call this bang-bang control. And often people figure this out just naturally, like this is a good way to control systems. But here it occurs very naturally from this optimization principle. Okay? So so whenever I have a limited axis of controls, this shows up example. And in our paper, we go through a lot more examples. We do some bosonic quantum computing examples involving squeeze states, Schrodinger cat states, Fock states. I won't go into all that, but if you're interested, you can take a look at the paper for those examples. And I think I'll stop there. So here are my conclusions. I told you about most likely path. I talked to you about continuous quantum measurements and some of the connections to these Schrodinger bridge problems. I didn't prove anything for you guys, but maybe this motivates you to work on this problem or related problems and formalize some of this stuff. It would be great. Thanks for your attention.